Hey guys, how you all doing? It's Jalajora here again, back with another video from BHM at GCSE Chem, and today we're going to be doing C4.1 Relative Masses and Moles. So that's what it's called, and so today we're starting chapter 4. We finished chapter 3 yesterday, so yeah. And by the way, I forgot to tell you, there weren't any keywords in the last section, which was there weren't any keywords to go through in C3.12 applications of nanoparticles. That's why I didn't mention it, but I just forgot to mention that there weren't any keywords. So yeah. And so today we're doing obviously chapter 4, C4.1, like the first section, which is obviously called Relative Masses and Moles. And again, I haven't been able to put the links to the videos of from C3.2 to C3.12, so I'll definitely try and put it today. I know I've been saying that for a long time, but I've been extremely busy. So much, I've been able to find time for these videos, but to make these videos, but not actually to put the links up. And so if you can hear any background noise as well, I've got my window open, by the way, because it's quite hot. So yeah, just if you can hear any noise of cars, I just heard a noise of a car, but yeah, going through. But yeah, and I haven't so I told you about the website. I'll try and put the links up, including C4.1 today. From C3.2 to C4.1, I'll put all those sections, the links to all those videos on my website today. Hopefully I'll be able to do that. And again, today I'm back in my own room, and not the living room or the lounge, because obviously today actually basically I've got my brother into making videos as well. So he makes videos, not obviously publishing them on YouTube because he's only 8 years old, but yeah, he really likes making videos on maths. He teaches maths, an 8-year-old, but yeah, it's great. He's got into this as well. He really likes making videos, and he's making a video right now, so I didn't want to disturb him downstairs, hence I came upstairs. But yeah, I think that intro has been quite long. So let's begin for the topic, which is C4.1 Relative Masses and Moles. And if you're following the student book, it's pages 62 to 63. Yep. And so we use the carbon atom, so let me begin. We use the carbon atom of, let me start again. We use the carbon atom of carbon 12, so that's C and then 12 on the top, 6 on the bottom, as the standard atom, and compare the masses of other atoms with carbon 12. So basically all you need to know that we use carbon 12 as a standard for all the kind of calculations that we do in chemistry. We use it as a standard, basically, as something that we can compare with. We use that as a standard. They might ask you which element do we use as a standard, basically, as a standard atom, and compare the masses of all the atoms with. It's carbon 12, and you write C and then 12 on the top and then 6 on the bottom. So the relative atomic mass takes into account of proportions of any isotopes of elements found naturally. So it's the mean relative mass of the atoms of elements compared with the standard carbon atom, which is assigned a value of exactly 12. Therefore, the relative atomic mass is not always whole number. For example, the AR, AR is basically how you write relative atomic mass. So that's A, which is capitals, and then subscript R. Which is little r, and so the AR of chlorine, or you could say the relative atomic mass of chlorine, is 35.5. So basically, if that didn't make sense, I'll explain it now, because we know that atoms of an element basically have there are different isotopes of each element, basically. Like for example, chlorine, you have chlorine 35 and chlorine 37, and basically chlorine 35 has an abundance of about 75%, and chlorine 37 has an abundance of 25%. So basically we take the weighted mean, so we take the the weighted relative mass of these two kind of isotopes, and that's why, because obviously there's a greater abundance of chlorine 35 than chlorine 37, obviously that should reflect in the relative atomic mass, which is 35.5. so it's closer to chlorine 35, it's close to 35 than it is to 37, because obviously chlorine 35 is more abundant than chlorine 37, because I just said chlorine 35 is about 75% abundant, and chlorine 37 is about 25% abundant. So yeah, sorry if you can hear any noise as well. But that's what it was basically talking about, and that's why relative atomic mass isn't always a whole number, because it's the weighted mean, it's the weighted kind of average of the the mass of the atoms of an element basically, and so that's why it could be a decimal number as well. And in which case, in chlorine's case, the relative atomic mass of chlorine is actually a decimal number. It's 35.5, and that relative atomic mass, which is AR, which I've just talked about, that's the notation you use, capital A and then subscript R, little r. That's actually on the periodic table. You find out which is the bigger number on the periodic table actually gives the relative atomic mass. So we've been through that in chapter 1 before, so I'm not going to go through that much. But yeah, so why is the relative atomic mass of chlorine not a whole number? We've just been through that. That's a question in this text, in this revision guide. Oh wait, have I shown you the revision guide I'm using? Sorry about that. I'm not going to start again, but this is the revision guide that I'm using, the AQA GCSE Chemistry revision guide from Caboodle. Yep, sorry if you can hear any noise from anyone's phones. I think there was just a phone buzzing there with a message, but yeah, it's not my phone, but I think it's my mum's phone or something. But where was I? So yeah, that's the book I'm using. I just showed you. I don't know why I showed you it late today in the video, but there you go. And then so why is the relative atomic mass of chlorine not a whole number? Well, we've been through that, because chlorine has two different isotopes, chlorine 35 and chlorine 37, and you take the weighted you take the weighted mass of the atoms of the elements basically, and and you take the weighted, basically it's based on the abundance. So that's kind of what the answer is. I'll tell you the exact answer, but that's kind of what you have to say in the exam. I'll tell you what the exact answer is. Hopefully that makes sense. What I've said is because of the different abundances, and it's the weighted mass of the atoms of the elements, and basically that's what the answer should be. For it's a C4.1 today we're on. Yeah, it has two main isotopes that I went through. I said chlorine 35, chlorine 37, and the relative atomic mass is the average value. So I said it's the average value of these two kind of isotopes, basically, of the relative atomic masses of basically the two isotopes. That's why it's an average. You take an average value of that, and that and you do it. You base and the abundance of each of the isotopes is taken into account. You can add that as well. That's why obviously we see that it's closer to 35 than it is to 37, because it's 35.5 for the relative atomic mass of chlorine, because obviously chlorine 35 is 75% abundant, as I've said before, and chlorine 37 is 25% abundant. So yeah, hopefully that makes sense. I think, have I missed anything? So yeah, there's two main isotopes, and relative atomic mass is an average value. So hopefully that makes sense. Yeah. Now the relative formula mass, we use the symbol MR. So for relative atomic mass it's AR, so capital A and then subscript R. Here for the relative formula mass, oh wait, before I forgot to do something as well here. Calculating, I'm forgetting things a lot today in this video, sorry guys. Calculating relative atomic mass. So chlorine has two isotopes, chlorine 35, and which is 75%, chlorine 37, which is percentage abundance of 25%. Calculate the relative atomic mass AR of chlorine. So this is the formula that you use basically. This is the calculation that you do. Chlorine 35 is an atomic mass of 35. You multiply by I'm doing this right. Yeah, you multiply it by its abundance, which is 75. You add that to the the relative atomic mass of the other isotope, which is chlorine 37. So 37 multiplied by its abundance, which is only 25, and you divide it by the total percentage. 100, and then you also that's what you do. You divide it by 100, and therefore you basically get your 35.5. So hopefully that makes sense. So basically, to generalize it, to work out the relative atomic mass, if you're given the abundances and the abundances and the masses of both the isotopes, you do the mass of isotope 1 times the abundance of isotope 1 plus mass of isotope 2 times abundance of isotope 2. Divided by the total percentage abundance, which is 100. So hopefully that makes sense. Now we're on to relative formula mass. So the relative formula mass of a substance is found by adding up. So relative formula mass is mR. So it's capital M and then subscript R. So yeah. And then, so the relative formula mass of a substance is found by adding up the AR of the atoms in the formula, and basically the AR is given by, or the relative atomic mass of each element is given by the, is on the periodic table, so you can use that basically in the exams to work it out. So in molecular substances such as CO2, you refer to the relative formula mass as the relative molecular mass, because obviously carbon dioxide, these are molecular substances. You have a molecule of carbon dioxide, a molecule of water. You refer to it as a relative molecular mass. It's not very important. Basically, the calculation is what's important. So what is the relative formula mass of sodium hydroxide? So this is a second question. And we've been given the relative atomic masses of sodium, which is 23, oxygen, which is 16, and hydrogen, which is 1. And if we've been through balancing, I think, have we been through creating formulas Na plus of C? We've been given the formula of sodium hydroxide. We don't even need to make it, but it's Na plus and OH minus gives NaOH. That's the formula of sodium hydroxide. But they've given it to us anyway. But Na is 23. Basically, because all these values given, Na is 23, O is 16, and hydrogen is 1. These are the relative atomic masses of sodium, oxygen, and hydrogen respectively. These are found from the top number in the periodic table of each element, basically. So 23 plus 16 plus 1 is 40. So the answer should be 40. And if they don't give you explicitly what the values are, just look at the periodic table. In this case, they gave what the values of each element was, but in the question they might not give it, in which case you just look at the periodic table that's provided to you in exams and work it out from there. It's always the top number of each element that gives you the relative atomic mass. We've been through that before, of each element, obviously. And so yeah, is it 40? Yes, it is. 23 plus 16 plus 1 is 40, just making sure. So and then here they give you another question. Here they give you another one, which is calculate the relative formula mass of calcium sulfate. So this isn't a question, actually. This is a worked example again. So we've been told calcium is 40. Sulfur is 32, oxygen is 16. We've been told the formula is CaSO4. So they might actually give you the formula, but they might ask you to work it out. I think we're going to look at working it out later. Maybe it might come later, but otherwise they probably will give it to you. But basically CaSO4, we said calcium was 40, sulfur was 32, oxygen 16, so you do 40 plus 32 plus 16 times 4, because there are 4 oxygens. So that would be 72 plus 64, which is 136. Yeah, so the relative formula mass of calcium sulfate, CaSO4 is 136, and hopefully that makes sense. Now we're looking at the mole, and the mole is only for higher tier students only, by the way. So chemical amounts are measured in moles, using mol as the symbol, so just MOL. Yep. 1 mole of any substance is the relative atomic mass or relative formula mass of the substance expressed in grams. For example, we just looked at calcium sulfate, CaSO4, that had a relative formula mass of 136. So that means 1 mole of calcium sulfate, basically 1 mole of calcium sulfate, 1 mole of the compound calcium sulfate basically weighs 136 grams. And we also looked at sodium hydroxide. So 1 mole of sodium hydroxide weighs 40 grams, because we obviously calculated its relative formula mass. Or we could use the relative atomic mass if we're given just a single element. Like what is the weight of how much does 1 mole of oxygen atoms oxygen molecules weigh? So you do 16 times 2 because it's O2, so then that would just be 32 grams. But what if it's just a single oxygen atom? Then it will be 16 grams. So it's obviously the relative atomic mass or the relative formula mass in grams is the weight of 1 mole of a substance. So hopefully that makes sense. A mole of any substance always contains the same number of molecules, atoms, molecules, or ions, and this is Avogadro's constant. Basically, this number is Avogadro's constant, which is 6.02 times 10 to the 23 atoms per mole. So so that's basically how many atoms there are in 1 mole. So, for example, in 1 mole of sodium atoms means there are 6.02 times 10 to the 23 atoms. That's the Avogadro's constant, basically. That's the Avogadro's number of atoms per mole, basically. Yeah. And to calculate the number of moles, we use these equations. So number of moles equals mass in grams divided by the relative formula mass, or the relative atomic mass. Or so it's either number of moles equals mass in grams over relative atomic mass, or the number of moles equals the mass in grams, which would be given to you in the question, or you might have to work it out if you're given the moles and the MR or the AR. So number of moles equals mass in grams over MR, or number of moles equals mass in grams over AR, depending on whether you're given the relative atomic mass AR or relative formula mass MR. So you use those equations. So this is just a recap. I'm not going through how you do this. It's just equations that you need to know and apply it. So you can rearrange the equations to calculate the mass of a certain number of moles. So we know mass, if number of moles equals mass over AR, then we know mass equals number of moles times AR. And if we have number of moles equals mass in grams over MR, then we know that mass in grams basically equals number of moles times MR. So hopefully that makes sense. And here's a third question: how many moles are present? Third and last question of the section. How many moles are present in 2.2 grams of carbon dioxide? We've been told the MR of CO2, which is 44, but you could have calculated that anyway because carbon is 12. Carbon has a relative atomic mass of 12. Oxygen is 16, but there are 2 oxygens, so that'll be 32. So 16 times 2 is 32. So 12 plus 32 gives you 44. So how many moles in 2.2 grams of carbon dioxide? Remember the formula: number of moles equals mass over MR. The mass is 2.2 grams over the MR, which is 44. I'm saying MR here because it's a compound, not a single atom that you're calculating. So so it's 2.2 divided by 44. It's the mass over the mass over the molar mass, mass over the molecular mass, MR, basically 2.2 over 44. So that should be 0.05, I believe, 0.05 moles. Hopefully that makes sense, and hopefully that is the answer. I don't want to be wrong here. Yeah, 0.05 moles, and you can just write mol, MOL for short. That's how you say it. Basically, that's how you express moles. You normally write MOL. And the synoptic links, for the one synoptic link in the section. For more information on isotopes and standard form, see topic C1.7. We've been through that before, C1.7, we've been through that. On the up as well, there's something here that you should be able to explain why relative atomic mass of some elements is not a whole number. We've been through that as well, about the weighted, about the mean mass, the atoms of an element that we use basically, and it's we take abundance into account, and we've been through all of that today. And the keywords in the section are relative atomic mass, which is capital A subscript R, relative formula mass, which is capital M subscript R. Subscript means a little number on the bottom of the big number, MR, and then mole and Avogadro constant. So that were the keywords. There are quite a few keywords in the section, and and so let's just finish off the section with key points. So the masses of atoms are compared by measuring them relative to atoms of carbon-12. So you just need to know that we use carbon-12 as a standard. They might ask you as a 1-mark question, what atom do we use as a standard? And we'll just use an atom of carbon-12 basically. And you can work out the relative formula mass of a compound by adding the relative atomic masses of the elements in its ratios shown by the formula. Yeah, and then basically the relative atomic masses of each of the elements are given on the periodic table, and you're given the periodic table in exams. So basically use it, and you just add up all these relative atomic masses. And if you have something like that is O2, you have to basically double that and then triple. If it's something 3 subscript 3, basically you do it in the ratios that are in the formula. So hopefully that makes sense. So if it's O2, you do 16 times 2, because the relative atomic mass of oxygen is 16, but you have 2 of them, so that's why it's 16 times 2. That's why we did, in carbon dioxide, we, for example, did carbon, which was 12, plus 16 times 2, because one oxygen atom is 16, but then there were 2, so that's why we had an oxygen molecule, in fact. So we had 16 times 2, which was 32, then 12 plus 32 gave 44 as the relative formula mass for carbon dioxide. So hopefully that makes sense. And then there are 3 higher points as well, only for higher tier students. And 1 mole of any substance is its relative formula mass in grams. We've been through that. 1 mole of carbon dioxide molecules would weigh 44 grams, because obviously the relative formula mass of, or you can say relative molecular mass of carbon dioxide is 44. 44 grams, by the way. And the number of moles is calculated by the mass in grams divided by the AR. Or the mass in grams divided by the MR. It's literally, you just add up the relative atomic masses, and that's how you get the MR basically. And so hopefully that makes sense. You use AR or MR depending on whether you're looking at atoms or you're looking at compounds. Basically, we've been through that. And the Avogadro constant is 6.02 times 10 to the 23 atoms per mole. So you need to know that as well. So hopefully this video has made sense. Hopefully this section has, hopefully this video has been really helpful to you guys. And that's the end of C4.1, relative masses in moles. Tomorrow I'll be doing C4.2, which is higher tier students only, actually, which is all about equations and calculations. So that's the end of the video, guys. Make sure to share, like, and subscribe. I really hope it was useful, as I said before. And what else do I say? I'll try to put the website all up to date, basically, with the links on the website up until C4.1, obviously. And make sure to turn the notifications on if you haven't already. Notification bell on if you haven't already, so you're notified and updated when I upload new videos that you can watch. And I don't think I have much more to say, other than also happy Independence Day. It's Independence Day for Pakistan, so I'd like to say happy Independence Day to everyone, actually, because I love Pakistan people. I'm Indian myself, but I just love unity between 2 countries, even though it's meant to be an Independence Day. Like, Indians love Pakistanis. That's what I go with. I believe in that. Just unity is the best. And so happy Independence Day. It's Pakistan's Independence Day, but literally to everyone, happy Independence Day. Tomorrow is Indian Independence Day, but there you go. And tomorrow we're going through C4.2, which is obviously equations and calculations. That's what it's called, and it's a higher tier topic only, so not for foundation tier students. Anyone doing foundation tier, you don't need to do that. And I think this video is getting a bit too long now, so I'll end it here. And thank you very much, guys.